Most of the time when you think of lung cancer, you probably think of cigarette smoking, as that is the most common cause of lung cancer, which means that you can dramatically reduce your risk by avoiding smoking. But there's another cancer of the tissues that surround the lungs that is caused by something that you didn't have as much control over, because before it was more tightly regulated, it was all around us, in our homes and in our places of work. And that is asbestos. And one of the reasons why asbestos came across our radar is that another YouTube channel called Veritasium was doing their own video on the history, regulations, and dangers of asbestos. So they reached out to us wanting to discuss how asbestos affects the lungs. So today, we're gonna go over what we talked about during that discussion by showing you that when this material gets disturbed, it becomes airborne and can lodge deep inside your airways. We'll show you how your immune system has trouble responding to this, how it can slowly scar your lung tissue, and how it can also lead to cancer. And of course, we'll briefly talk about when asbestos was regulated in the United States, what that means if you live in an older home, and how to think about your own risk of exposure. It's going to be a fibrous one. So let's get into this anatomical and physiological awesomeness. But before we look at the anatomy, let's define what asbestos actually is. Asbestos is not a chemical or a gas. It's a group of naturally occurring mineral fibers. For decades, it was used in insulation, fireproofing materials, flooring, and roofing because it's heat resistant and very durable. The problem is when those materials are disturbed, microscopic fibers become airborne, and once inhaled, they can travel deep into the respiratory system. There are two broad fiber categories that you'll often hear about: serpentine fibers, like chrysotile fibers, which are more curly, and amphibole fibers, which are straight, needle-like, and more biopersistent. The shape and durability actually matter because once those fibers enter your airway, aerodynamics and biopersistence determine how deep they go and influence your body's ability to clear them. So let's look at the pathway that these fibers would take once they're inhaled, and you could actually apply this to any harmful substance that you've inhaled. But when we inhale, air enters through the nose or the mouth, and if you take a look at this sagittal head dissection, if we breathed in through the nose, air would enter into the nasal cavity. And you can see my probe is in the left side of the nasal cavity. And here's the nasal septum that would divide the cavity into right and left sides. That air moves posteriorly to the pharynx, which is just a fancy pants name for the throat. And then the air will move downward and we get to a fork in the road. Posteriorly, we have the esophagus, the food tube. And asbestos fibers can actually get swallowed in some cases. But in those cases, a lot of the fibers will just pass through the digestive tract and be eliminated in the stool. But sometimes the fibers can get deposited in the tissue of the digestive tract, and this is one of the proposed ways that we can get asbestos-related cancer forming outside of the lungs, which we'll talk a little bit more about later. But the majority of the asbestos will continue down the respiratory tract anteriorly. Here you can see the larynx, or sometimes referred to as the Adam's apple or the voice box, and below you can see the trachea, often referred to as the windpipe. Now you might have noticed that the esophagus is collapsed, but even on a cadaver, the trachea remains open. And that is because of these cool little cartilaginous rings that you can see stacked on top of each other. With the esophagus, we don't care that it collapses between meals. We don't need to be eating 24/7 in order to stay alive. But with the trachea, we do need it to remain open 24/7 because we're breathing all the time. And I probably should be a little more specific and say C-shaped or horseshoe-shaped rings because these cartilaginous rings don't actually come together in the back. But if you look at this fully intact larynx and trachea, you can see again those cartilaginous rings just stacked on top of each other. But look how cool it is when I turn it around. You can see that the rings don't come together on the back and they're more C-shaped. So it's really easy to tell an anterior view from a posterior view of a trachea. But this tissue between is also worth mentioning. This is called the fibromuscular membrane, and it contains smooth muscle. So even though the airway is open 24/7, the trachea can change its diameter based on smooth muscle contractions within this membrane. This smooth muscle even continues down into the smaller airways. And as a fun little FYI, for those that have ever experienced an asthma attack, the smooth muscle in those smaller airways can spasm, narrowing the airways, making it much more difficult to breathe. But coming back to the pathway of asbestos, as the air travels down the trachea, it passes over an important defense system. If we open up this other trachea that's still attached to the lungs here, But if we look at the inside, we can see the inner lining of the trachea. This inner lining is called the tunica mucosa, as it produces mucus, and it's made of tall columnar epithelial cells with cilia on their surface. You also have goblet cells that are secreting mucus. This combination forms what's often called the mucociliary escalator. Particles will get trapped in the mucus, and then the cilia will beat upwards. And that little mucus ball will eventually get pushed up towards the throat. And once it reaches your throat, you have an important choice to make. Either you cough it out, or you swallow it. Now, some people will say, if you swallow it, doesn't that defeat the purpose? And the answer is no, not really, because you are moving it out of your respiratory passageways and into a different system, the digestive system, which tends to not be harmed as much by particles that could irritate the respiratory system. But these mucociliary mechanisms in the respiratory system are incredibly effective at clearing inhaled debris. But it's not perfect, and we'll see why it has some limitations with asbestos as we go deeper down. The trachea will branch into right and left main or principal bronchi to direct air to the right lung or the left lung. The bronchi, as you can see on this other cadaver dissection, will continue to branch until they branch into smaller airways referred to as bronchioles. And just to make sure we know how remarkable this is, we are going to go through about 23 generations of branching. If you've ever done 2 times 2 on a calculator and then hit equals over and over and over again, if you do that over 20 times, you are in the millions. And so by the time we reach the smallest airways, the alveolar sacs and alveoli, we're dealing with millions of microscopic tubes. And that's incredible for increasing the surface area for the most efficient exchange of carbon dioxide and oxygen between the alveoli and the bloodstream. But here's what changes and is important to our story. As we move deeper into the lungs, the epithelial lining within those tubes changes. Remember, they started as tall ciliated cells coated in mucus. However, as we move further down, those cells gradually become more cube-shaped, and in the smallest bronchioles, alveolar ducts, and alveoli, the cells flatten out, and they start to lose their cilia. That means if particles make it past the upper airway defenses and reach those lower regions, you've lost the mucociliary escalator, and again, this is where asbestos fiber shape and size matters. Those curly chrysotile fibers are more likely to get trapped higher up, but the straight, needle-like amphibole fibers can travel deeper. I kind of think of them as straight, like they're straight little arrows that kind of shoot past the upper airway defenses and don't get caught in the mucus-covered cilia. And so those amphibole fibers are much more likely to deposit lower down at the airway bifurcations and lodge in tissue. And once the fibers are in the deeper airways, they are extremely biopersistent, meaning they don't dissolve easily and they resist enzymatic breakdown. So now we have a fiber embedded in the tubing and even potentially working its way into the surrounding lung tissue. And the immune system is about to respond. When asbestos fibers lodge in the tubing or in the surrounding lung tissue, your immune system does what it's supposed to do. Macrophages, which are white blood cells, arrive at the site. Their job is to engulf foreign material through a process called phagocytosis, which translates to cellular eating. If the fiber is small enough, the macrophages may be able to engulf it, but even then, they struggle to break it down. And if the fiber is long, especially those straight amphibole fibers, the macrophage can't fully engulf it. And this leads to something called frustrated phagocytosis. The macrophage tries to engulf it, but fails. And in this frustrated process, it releases reactive oxygen species, which are free radicals. And those molecules can damage surrounding cells, cellular membranes, and importantly, they can damage DNA, which will be more important here in just a minute. And at the same time, inflammatory signals released by the macrophages recruit more immune cells to the area, but none of them have much success with eliminating the fiber. So instead of resolution, you get chronic inflammation. And whenever you get chronic inflammation, other cells called fibroblasts get recruited. And fibroblasts produce collagen, which excessive collagen deposition leads to scar tissue formation. Over years, sometimes decades, this chronic inflammatory process can lead to fibrosis or scarring of the lungs. And scarring of the lungs due to asbestos is referred to as asbestosis. And here's what that does mechanically. Normal lung tissue is incredibly compliant, meaning it stretches and recoils with each breath. And students just love touching lungs in the lab due to this gushy, compliant nature. But if fibrosis develops within the lung tissue, it stiffens the lung. So now you have reduced compliance, the lung doesn't expand as easily, they don't recoil as efficiently, and this can restrict breathing. In mild cases, someone might have small areas of scarring and minimal to no symptoms. In more severe cases, the fibrosis progresses and breathing becomes significantly impaired. And asbestosis is not curable. Once that scar tissue forms, it does not reverse. So treatment focuses on supportive care and preventing further damage. That means eliminating ongoing exposure, monitoring lung function, and managing symptoms. In more advanced cases, patients may require supplemental oxygen, and in very rare situations, lung transplantation has been performed. But again, that is relatively uncommon. But that's just one pathway that asbestos can take. There's another structure involved that we need to learn about because this structure is extremely relevant to asbestos exposure leading to cancer. If we come to this thoracic cavity dissection, you can see the lungs sitting inside the chest. Now, if we were to take a chest x-ray of you and there was this much space between your lungs and the inside of the chest wall, that would be a major problem because these lungs are most definitely collapsed. But with you, the lungs will be pushed up to this membrane that you can see lining the inside of the chest wall with a little bit of fluid in between called pleural fluid. That fluid helps reduce the friction between the lung and the inside of the chest wall. And if you've ever put two pieces of glass together with a little bit of fluid in between, you'll notice that this causes the two pieces of glass to stick together, but you can still slide them against each other. And so the pleural fluid also helps create some surface tension to help the lung maintain its contact with the inside of the chest wall. But this membrane lining the chest wall is very important to our cancer story and is referred to as the pleural membrane. And it is actually continuous with the lungs. The layer directly covering the lung, but you can see some of that tissue coming on and blending onto the lung, this is called the visceral pleura. The layer lining the chest wall is the parietal pleura, which makes sense because visceral means organ and parietal refers to wall. But if we were to zoom into both tissue layers, we would see that they are composed of a single layer of cells called mesothelium. These mesothelial cells are the cells that secrete the lubricating pleural fluid. But here's where asbestos becomes especially concerning. Fibers embedded in the lung tissue can migrate directly outward towards the pleura, either the visceral pleura or the parietal pleura, or they can get there through lymphatic transport or macrophage movement. And this can irritate those mesothelial cells, which can trigger chronic inflammation. And with repeated oxidative stress, this can result in DNA damage. And over time, if enough mutations in the DNA of those mesothelial cells accumulates, especially mutations that affects the genes that regulate cell division, those cells can begin dividing uncontrollably, and this can lead to cancer. Mesothelioma is a malignant cancer of mesothelial cells, and while asbestos exposure has been associated with multiple cancers, mesothelioma is the one that's most strongly linked to it. Now, we just discussed pleural mesothelioma, or mesothelioma of the tissues surrounding the lungs. And this is the most common location of mesothelioma due to asbestos exposure. However, mesothelial cells don't just make up the pleural membranes. They are found in other regions of the body. Like mesothelial cells make up the lining of the abdominal cavity. And so you can get mesothelioma in the abdomen due to asbestos exposure. Now, you might be wondering, how in the world do asbestos fibers get into the abdomen and cause cancer of those mesothelial cells? Well, there are two potential mechanisms for this. One, if you recall, some asbestos fibers can get swallowed and in some cases may translocate through the digestive tract and into surrounding tissues. And this is a potential way for mesothelioma developing within the abdomen. And secondly, if you remember, macrophages can't successfully break down the asbestos fibers, but they can fully engulf smaller fibers or even partly engulf some larger fibers. And those macrophages don't necessarily stay within the lungs. The macrophages and even non-engulfed asbestos fibers in the lungs can move into the lymphatic vessels. And once you get into the lymphatics, you can potentially go anywhere throughout the body, including the abdomen. And it's almost as if you've just transported this problem of not being able to break down and fully engulf the asbestos fibers to a new location, where the inflammatory process and the release of free radicals now takes place somewhere else. And it doesn't even just cause mesothelioma of the abdomen. It's even been associated in some studies with cancers like ovarian cancer. Now, one last important thing to note is that often people will assume that asbestosis, that condition of scarring within the lungs, is a stepping stone or precursor to mesothelioma. And that is not the case. Yes, in some cases they can coexist, but they arise through different pathological mechanisms. So just because someone gets asbestosis doesn't mean they are going to develop mesothelioma. Yes, their risk of mesothelioma is higher, but that risk comes more from the exposure to asbestos rather than whether or not they developed asbestosis. Now, before we finish up, it's worth briefly talking about when asbestos was regulated and what that means for your own risk of exposure. Because when I first started having these discussions with Veritasium while they were prepping for their video, I was like, I'm doing some major home renovations right now. My house was built in 1982, so should I be worried? Well, it depends on the materials used and whether they're being disturbed. Asbestos use in the United States peaked in the mid-20th century and was heavily regulated beginning in the 1970s and 1980s. Many common residential products that once contained asbestos, like insulation, floor tiles, and roofing materials, are no longer being manufactured with it. However, because asbestos was used so widely for such a long time, it's still present in many older buildings, especially in homes, schools, and commercial structures built before the 1980s. So if you live in an older house or are renovating a building from that era, it's important to be aware of where asbestos might be hiding. Things like the attic or wall insulation, floor tiles and adhesives, roofing and siding shingles, pipe insulation, and boiler lagging. And so if you suspect any of these materials might contain asbestos, the safe thing to do is to not disturb it yourself. Asbestos is most dangerous when it's released into the air as fine fibers. That's why professionals use special equipment and containment procedures to safely remove it or encapsulate it. In everyday life, the biggest risk comes from disturbing old insulation, sanding, cutting, or demolishing old materials, and cleaning up debris from renovation without protection. For most people in modern buildings, asbestos exposure risk is very low, especially if materials are intact and undisturbed. But if you're doing renovations on older structures, it's worth having materials tested and, if necessary, handled by licensed abatement professionals. I'm assuming that many of you watching our content are a little nerdy and love to learn. I'm the same way, but I'm a little heavy in the biological sciences, so I love to challenge myself in other subjects, and that is why I use Brilliant. Brilliant helps you excel in math, coding, data analysis, science, and even AI. And their courses are crafted by an award-winning team from places like MIT and Caltech, and are designed for ages 10 to 110, if you are lucky to live that long. But this means Brilliant starts you at the right level based on your background, with practice sets and end-of-level reviews personalized just for you. I've personally been using Brilliant to sharpen my math skills and have been using their lessons on exponential functions, and have been loving how Brilliant helps you excel through visual, interactive problem solving, and personalized practice that builds genuine understanding. Now, another reason I think Brilliant is beneficial for our audience is that many of our viewers are looking to go into the medical field. And going into the medical field requires more than biological knowledge. You'll have to take math, statistics, and review research. And so Brilliant's got you covered with lessons that build the foundation for the math and data analysis that you'll need. Plus, since most users learn on their phones, it's seamless to jump on at any time. So if you want to learn for free on Brilliant for a full 30 days, go to brilliant.org/IHA, scan the QR code on screen, or click the link in the description. Brilliant is also giving our viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. Thanks again to Brilliant for sponsoring today's video, and if you want to check out Veritasium's video, we'll also have that below. Thanks for watching and supporting our channel, everyone, and we'll see you soon.